Every year, cities spend billions patching the exact same potholes. Modern asphalt is designed to grip, but under the constant punishing weight of heavy trucks, the surface inevitably gives way, cracking and crumbling into craters. Now, look at the dome of the Pantheon in Rome. It's built entirely of unreinforced concrete, exposed to the elements, and it has stood perfectly intact since the year 128. Recently, researchers at MIT analyzed samples of this ancient material and discovered something remarkable. When Roman concrete cracks, it literally grows new crystalline minerals to seal the fissure shut. 2 millennia ago, builders engineered a self-healing material that modern science is only just now figuring out how to replicate. How did they do it? For decades, historians assumed the Romans were just sloppy mixers. Ancient mortar is speckled with tiny, bright white chunks of calcium called limeclasts. Modern concrete standards actually consider these unmixed chunks a structural flaw. When a crack forms and rainwater seeps in, it hits the limeclast first, dissolving the calcium into a reactive liquid. This fluid spreads through the fissure and hardens into solid calcium carbonate, bridging the gap before the crack expands. Modern concrete treats water as an enemy that wests internal rebar and widens fractures. Instead, the Romans weaponized water, turning the rain itself into the catalyst for an automatic chemical repair system. This chemical resilience was supported by a brutal physical geometry. Roman engineers favored strict straight lines, cutting paths directly through mountain slopes, and elevating causeways over sinking marshes to guarantee the shortest possible distance. To ensure stability, they built the roadbed in 4 distinct layers: heavy base stones, rubble, pounded concrete, and fitted paving blocks. An elliptical surface forced rainwater into side gutters, while the dense foundation distributed the massive weight of passing legions. The Roman road was an integrated machine. The surface geometry repelled standing water, the sublayers handled physical impact, and the chemistry healed microscopic damage. The state poured massive resources into this infrastructure to support the cursus publicus, the state-run transport system. At its peak, this road network sprawled across 400,000 kilometers and linked 113 distinct provinces, from Britain to North Africa. To keep information moving efficiently, the government set up relay stations, called mansiones, at precise day-long intervals, guaranteeing fresh horses, blacksmiths, and secure lodging for official couriers. Markers like this surviving milestone tracked the progress of messengers, who could cover up to 100 miles in a single day. In the ancient world, this was the absolute physical speed limit of information. Because of this velocity, the cursus publicus functioned as an imperial intelligence agency. A revolt in Syria could be reported to the emperor in Rome weeks before local governors could even organize their own responses. The roads were the central nervous system of the empire. They enabled a concentration of military and administrative control that kept a sprawling, diverse continent governed by a single city for hundreds of years. Today, material science startups are taking the exact chemical signatures found in those Roman limeclasts and integrating them into modern commercial cement mixes. This industrial plant highlights the stakes. Modern cement production is responsible for about 8% of global carbon emissions. By engineering concrete that fixes its own cracks, we drastically cut down on the need to manufacture replacement materials. Our modern impulse is often to solve infrastructure problems with more complex mechanical solutions or synthetic polymers. But studying these ancient roads proves that we can achieve extreme durability by simply rethinking the underlying chemistry of the materials we already use. These ancient ruins provide a functional blueprint for self-healing infrastructure, challenging us to build for eternity rather than for the next decade.